These mortals have awakened the gods of old. We rise from our slumber to reveal our true power. Focus fire. To strike. To strike.
last night. Maybe I can make it right. Sit down closer, baby. We can talk about it. No need to be mad. Hate to see you sad. Yes, I know I'm crazy, crazy about you, crazy about you.
I know I'm a flirt sometimes. I know I get drunk some nights. I know I get way too high. I just wanna live it up with you. I know that it might be tough. I know when you've had enough. It's just how I show my love. Darling, can I live it up with you?
Last night. Maybe I can make it right. Sit down closer, baby. We can talk about it.
Made a mistake last night. Maybe I can make it right. Sit down closer, baby. We can talk about it. No need to be mad. Hate to see you sad. Yes, I know I'm crazy, crazy about you, crazy about your love. I know I'm a flirt sometimes. I know I get drunk some nights. I know I get way too high. I just wanna live it up with you. I know that it might be tough. I know when you've had enough. It's just how I show
Get ready to embark on an epic game development journey and recreate the most popular game ever created, Tetris. With just a few hours of your time, you'll be able to create your very own fully functional and engaging Tetris game using the C++ programming language and the Raylib library. Join me as I take you step by step through the process, from setting up the game loop to creating the game grid and blocks, to implementing movement, collision detection, and scoring. You will learn invaluable game development concepts and techniques along the way, and by the end of this tutorial, you'll have a polished and exciting Tetris game that you can proudly share with the world. To make sure you don't miss out on any updates and new tutorials, be sure to subscribe to my channel and hit that like button to show your support. So, what are you waiting for? Let's dive into the world of Tetris game development together. Subscribe now and let's get started. But why build Tetris on your own if tools like ChatGPT can build it for you in seconds? In today's world of constant distractions, shortened attention spans, and easy access to AI tools, it is more important than ever to develop the ability to focus on a complex task and see it through to completion. Building a game like Tetris from scratch will challenge you to break down a complex problem into manageable steps, strengthen your problem-solving skills, and improve your ability to concentrate on a project from start to finish. Today, there are so many distractions vying for our attention, from social media notifications to instant messaging, that it can be difficult to concentrate on any one task for an extended period of time. However, the ability to concentrate is crucial for success in any field, including game development. Without focus, it is easy to become overwhelmed by the complexity of a project like Tetris and give up before completing it. As my favorite thinker, Charlie Munger, said, "I succeeded because I have a long attention span." Google Charlie Munger to see how successful he is and what he has accomplished. Long attention span and focus lead to success. Not to mention the satisfaction that comes with creating something entirely from your own ideas and hard work. I promise you, if you complete this tutorial, you are going to feel very happy. Trust me. Also, learning to build a Tetris game using C++ and Raylib is a great way to improve your coding skills and expand your knowledge of game development. By following this tutorial, you'll be able to learn the fundamentals of C++ programming, such as loops, conditionals, functions, and object-oriented programming. You'll also gain experience with Raylib, a powerful library for building 2D games in C++. In order to follow this tutorial, I expect you to have a basic knowledge of the C++ programming language and a development environment for C++ already installed. I am going to work with Visual Studio Code. Lastly, we're going to need the Raylib library. I have prepared a detailed video on how to install Raylib on your Windows computer and use it with Visual Studio Code. You can watch it here. It will help you set up everything on your Windows computer. If you prefer to use Visual Studio, check out the second tutorial I have prepared. It will be linked in the video description as well. If you use a different operating system, you can still follow this tutorial if you have a working C++ setup with the Raylib library. Additionally, if you are new to game development with Raylib, I suggest starting out with our Pong and Snake game tutorials, also linked in the video description, to make the learning process smoother. Don't worry if you are not yet an expert in C++. This tutorial will provide valuable insights and help you learn a lot. So if you have set up everything and you can compile and run a simple Raylib example program, we are ready to go. As Lao Tse once said, the journey of 1,000 miles begins with a single step. So let's take that first step towards creating our own Tetris game and see where this journey takes us. Tetris may seem complex and challenging to develop, but fear not. We will take a divide and conquer approach to make it more manageable. In this tutorial, we will break the development process down into 12 steps, tackling each one individually and building upon what we have accomplished in previous steps. With this approach, you'll be well on your way to creating your own Tetris game in no time. So let's get started and see how we can conquer this challenging project one step at a time. The first step in building our Tetris game is to create a blank screen and set up the game loop. Before we start, it is important to understand the structure of a game. Every game consists of two parts: the part where we define our variables and game objects, such as the grid, the blocks, and the user interface, and the game loop, which is responsible for updating the positions of the game objects and checking for collisions. The game loop is like the heartbeat of the game, running repeatedly until the game is closed. In each iteration of the game loop, we will draw the game objects in their new positions and check for collisions, all happening so fast that it appears as a continuous movement. Now, let's create a blank screen and the game loop. Let's open the C++ starter template for Raylib that I have created with VS Code. You can download this template project by visiting this GitHub repository. If you open this template with Visual Studio Code, you can see it is organized in folders. We have to open the source folder and double-click on the main.cpp file. If we now compile and run this project by pressing F5 on the keyboard, it displays a bouncing ball example. Cool, our setup works. We are ready to start developing our game. Let's delete the bol.h and bol.cpp files and all the code from the main.cpp file. Just leave the include Raylib line and the main function just like I did. Now let's create a blank screen for our game and the game loop. First of all, we have to create our game window. The game window is like a black canvas where we can draw our game object. We need to specify the width and the height of the game window. I am going to use a size of 300 by 600 pixels for now. We will We'll change that later. To create the game window, we have to call the initWindow function. This function initializes a window and takes three arguments: the width and the height of the window and the title. For the width and the height, let's enter 300 by 600, and for the title of the window, let's enter Raylib Tetris. Now, every time we create a window, at some point, we have to destroy it, and we do so with the close window function. So, let's add the close window function here. We just created a game window, and to draw in it, we use a coordinate system similar to the one taught in high school. Each point on this window has its unique x and y values. The coordinate system used in computer graphics differs from the standard Cartesian coordinate system taught in high school. In computer graphics, the origin of the display is located at the top left corner, with 0, 0 being at the top left. In contrast, the standard Cartesian coordinate system starts from the bottom left corner, with 0, 0 being the origin. In this system, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move up. However, in the top left corner coordinate system used in computer graphics, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move down. This means that a point at 10, 10 will be located 10 units to the right and 10 units down from the origin. We will be using the top left corner coordinate system in our Tetris game. That's why it is important to understand the differences between these two coordinate systems. The basic setup of the game is ready. Let's now work on the game loop. The game loop consists of three parts: event handling. First, we need to check for any events that occur in the game, such as quitting the game, a key pressed on the keyboard, etc. Updating positions. Next, we update the positions of all the game objects, such as the block, based on the events we detected in step number 1. Drawing objects. Finally, we draw all the game objects in their new positions on the screen. This step uses the Raylib graphics functions to render the objects on the display. By following these three steps, we can create a dynamic and interactive game that responds to the user inputs and updates its state accordingly. We start the game loop with a while loop like this: while, parentheses, and curly brackets. The while loop will run over and over again until we close the game. The first thing we do inside the game loop is to check for any events. Now, inside the parentheses, we type the condition: window should close parenthesis equals false. The window should close Raylib function is a very useful function. It checks if the escape key on the keyboard is pressed or if the close icon of the window is pressed and returns true if that is the case. So if it returns true, the game loop ends and the window is destroyed. Our game loop needs two more functions. First, we need to call the begin drawing function. This function creates a blank canvas so we can draw our game objects on. Next, we need to call the end drawing function, which ends the canvas drawing. Lastly, there is something else we need to do. We have to define how fast the game should run. We do so by calling the setTargetFPS function before the game loop. The setTargetFPS function takes an integer as an argument, and that integer is the number of frames per second that we want. I'm going to use 60 frames per second. setTargetFPS 60. That's it. If we don't define a frame rate for our game, the computer will try to run the game as fast as it can, so the game speed will depend on the speed of the computer. By defining a frame rate, we make sure that the game runs at the same speed on every computer. For this game, we define that we want to run this while loop and update the display 60 times per second. Now that the game loop is complete, we can run the game for the first time. If we run the game at this point, we won't see anything inside the game window because we haven't drawn anything yet. But the important thing is that we can see the game window with the title and the dimensions we defined, and that we can reliably close the game by clicking on this X icon here or the escape button on the keyboard. Cool, but the game window is black. Let's give it a dark blue color. Raylib provides several built-in colors, but we will be defining our own colors for this game. In Raylib, colors are represented using a struct called color, which contains 4 unsigned byte components: red, green, blue, and alpha. The values for each component range from 0 to 200. Give it a dark blue color. Raylib provides several built-in colors, but we will be defining our own colors for this game. In Raylib, colors are represented using a struct called color, which contains 4 unsigned byte components: red, green, blue, and alpha. The values for each component range from 0 to 255, where 0 represents the absence of the color and 255 represents the full intensity of the color. For example, to create a red color, you will create a color struct with the following values: color red equals to curly brackets 255, and 255 represents the full intensity of the color. For example, to create a red color, you will create a color struct with the following values: color red equals to curly brackets 255, 0, 0, 255. The first three values represent the red, green, and blue components respectively, while the fourth value represents the alpha component, or the transparency of the color. In this case, the alpha value is set to 255, which means the color is completely opaque. So to create a dark blue color, we will create a color struct like this: color dark blue is equal to curly brackets 44, 44, 127, 255. Inside the game loop, before the endDrawing function, we call the clear background function. Clear background, parenthesis, dark blue. So when the clear background function is called, the Windows background is cleared with this blue color. This is typically done at the start of each frame of the game loop, so that the previous frame's graphics are wiped clean, and that the new frame can be drawn without any old artifacts or remnants. If we run the game now, we can see the game window is now dark blue. Beautiful. We just completed a very basic game loop, so we can remove step number 1 from our list. We have made progress. Let's now work on step number 2. To prepare for remove step number 1 from our list. We have made progress. Let's now work on step number 2. To prepare for writing code, it is important to take a step back and think through the game logic thoroughly. In Tetris, the gameplay area is a grid consisting of 20 rows and 10 columns. The game pieces, or tetrominos, fall down the grid, and the player must arrange them to form complete rows without any gaps. We will count the rows from the top to the bottom and the columns from left to right, with the top left cell at row 0 and column 0 being the origin. To represent the grid, we will use a two-dimensional array. In our implementation, empty cells will be represented by the value 0. When a tetromino, a block, is permanently placed on the grid by the player, the corresponding cells will be assigned a value reflecting its color. For example, if we place a red tetromino on the grid, we will assign the value 2 to the cells it covers. Similarly, if we place a yellow block, we will assign the value 4 to its corresponding cells. Each color has a unique numerical value, and since there are 7 different colors in the game, the values used in the 2D array will range from 0 to 7. 0 for an empty cell, and 1 to 7 for the colors of the blocks. So if the game state at some point is something like this, the two-dimensional array will look like this. However, the current block that can still be controlled by the player will not be reflected in the array, and will instead be stored and managed separately in the game logic. Now that we have a clear understanding of the game grid, we can begin implementing it in code. Let's go back to our code. We are going to use object-oriented programming to help us organize our code. We will create a grid class. As we are creating a separate class for our game grid, we need to separate the declaration of the class and its implementation. This is where the header file and the implementation file come into play. The header file, usually with a .h extension, contains the class declaration, including the class name, member variables, and function prototypes. It serves as an interface for other parts of the program to use the class. On the other hand, the implementation file, usually with a .cpp extension, contains the actual implementation of the class functions. This is where the member functions defined in the header file are implemented. Separating the class declaration from its implementation allows for better organization and abstraction of code, making it easier to manage and maintain large projects. So we will need to create 2 new files to create the grid class. I press Ctrl+N to create a new file, and then Ctrl+S to save it as grid.h. Now we can start writing the header file of our grid class. Sharp pragma once. This is an instruction that ensures that this header file is only included once in a compilation unit to avoid duplicate definitions. Now we can define our class grid, curly brackets, and a semicolon. Our class will have some public and some private methods. So let's add public colon here and private colon here. Now the first public method is going to be a constructor. So we type grid, parentheses, and a semicolon here. Now, what do we want to know about the grid? First, we need to know how many rows and how many columns it contains. So let's create 2 attributes to store this information. Do the other parts of our game need to know how many rows and columns the grid has? Probably not. So let's declare these attributes as private. Int num rows, int num columns. Next, we need to know the size of each cell of the grid in pixels. Int cell size. Now we need a two-dimensional array to represent the grid itself. Let's make this attribute public for now because we're going to need to modify the grid for testing. Int grid brackets 20 brackets 10. We declare an int array with 20 rows and 10 columns. Now let's work on the implementation of the grid class. Let's create a new file, Ctrl+N, and then Ctrl+S, and rename it grid.cpp. The first thing we have to do is to include the header file we created a few minutes ago. Include grid.h. Now we need to implement the constructor that will initialize all the attributes. Grid, colon, grid, parentheses, and curly brackets. Num rows equals 20, num cols equals 10. Now let's make the cell size to be 30 pixels. Cell size equals 30. The next step is to initialize the grid array with zeros. For that, let's create another method and call it initialize. So we have to go back to the header file. We can press Alt+2 and go back to it at once. It is the second open tab in VS Code, so we can use this keyboard shortcut if we wish. This method is going to be public because we are going to use it from other parts of the program. So we type here, void initialize. Now back to the implementation file, Alt+3. Let's implement this method. Void grid, initialize, parentheses, and curly brackets. Now we need to loop through all the elements of the array and give them the value 0. For int row equals 0, row less than number of rows, row plus plus. For int column equals 0, column less than number of cols, column plus plus. Grid, brackets, row, brackets, column equals 0. Let's call this method in the constructor. We type initialize here. Now that the grid is full of zeros, let's print it at the terminal to see if it works. Let's create a method for it. Again, back to the header file. Let's create a public method named print. Void print. Now in the implementation file, we create the method implementation. Void grid, print, parentheses, and curly brackets. Again, we have to loop through all the elements of the grid and print the value of each one at the terminal. For int row equals 0, row less than number of rows, row plus plus. For int column equals 0, column less than number of cols, column plus plus. Now we need to print each value, so let's include a library for this. At the top of the file, we type include IO stream. Back to our method now. std cout grid brackets row brackets column and a space in quotes. And outside the second for loop, std cout std end line. That's it. The method is ready. This method will be useful if we want to see the state of our grid later on. Let's now create a grid object in the main file and print it to see if everything works as expected. Alt+1 to go back to the main file. Now we have to import the grid class. So include quotes grid.h. Now we can create a grid object. Grid equals grid. Now we can call the print method, grid.print. And now let's run the program. Cool, as you can see, at the terminal, we can see all the contents of the grid. A 2D array filled with 0. Our grid is ready. Now let's go back to the grid class to work on it a little more. At +2 and VS Code gets me back to the grid class header file. What else do we want the grid to know about? The grid must also know the colors to use to display each cell. So let's create a data structure to hold all the colors it will use. The easiest C++ data structure we can use is a vector. A C++ vector is a container that can hold multiple values of the same data type, like a list or an array, but with some additional features, such as the ability to easily add or remove elements and to dynamically resize itself. To use a vector, we first have to include it. So we type include vector at the top of the file. We also need to include the Raylib library, since the vector is going to hold color structs from the Raylib library. So we type include raylib.h. Now we are ready to define the vector attribute. Let's make it private. std : vector color colors. As we said, we have 7 blocks in the Tetris game, and each block has its unique color. So we're going to need 7 colors for the cells of the blocks and 1 color for the empty cell, a dark gray color. Let's create a method that will return a vector containing 8 colors, and let's make it private. std : vector color get cell colors parentheses. Now let's go to the implementation file to create the method and the colors. std : vector color grid : get cell colors parentheses and curly brackets. As we said, a color is just a struct of 4 values. So let's create the structs. Here are all the colors. I have created a struct of type color for each color and a struct for the color of the empty cell, this one. Now let's put all of them in a vector and return that vector. Return curly brackets, dark gray, green, red, orange, yellow, purple, cyan, blue. The order of the colors in the vector is important. We are going to use the index of each color later on when we draw each cell on the screen. The index corresponds to the block ID, but more on that in a minute. So in the constructor, we can now load the list of colors. Colors is equal to get cell colors. That's it. The constructor method of the grid class is ready. Now we are ready to draw the grid. Let's create a draw method. Back to the header file. The draw method is going to be public. Void draw. Now back to the implementation. Void grid, : draw, parentheses and curly brackets. We need to draw each cell of the grid with a specific color. With dark gray color if the cell contains 0, with green color if the cell contains the value 1, and so on. So first we have to get the value stored in each cell of the grid. We will use a nested for loop for this. For int row equals 0, row less than number of rows, row plus plus. For int column equals 0, column less than number of columns, column plus plus. Int cell value is equal to grid brackets row brackets column. This code iterates through each cell in the grid and assigns the value of that cell to the variable cell value. Now it is time to draw this cell on the screen and give it a color. Now before we draw something, let's talk about how Raylib draws simple shapes on the screen. Raylib provides various functions to draw simple shapes on the screen, including rectangles, circles, lines, and polygons. When using any of these functions, you need to specify where on the screen you want the shape to be drawn. For instance, to draw a square, we can use the draw rectangle function. This function takes 5 arguments: the x and y coordinate of the top left corner of the square, the width and the height of the square, and a color. In our game, the cells are square, so we will use the draw rectangle function to draw the cells of the grid. Let's go back to our code. So inside the draw method of our grid object, let's draw a square. Draw rectangle, parentheses, x, y, w, h, color. We need to know 5 things to draw a cell of the grid as a square. The x and y coordinate of its top left corner, its width, its height, and its color. The x is going to be column, but since we're using a grid, we have to multiply this by cell size. Column times cell size. We do the same thing for the y. Row times cell size. Now the width is going to be cell size, and the height is also going to be cell size. The last argument we have to provide is the color. The color is a color stored at the colors vector. But which one? We can use the cell value variable to index into the colors vector and retrieve the color struct for that specific cell. So we type colors brackets cell value. Since our grid now only contains zeros, the cell value variable will be 0. So this will return the first color of the vector, which is a dark gray color. That's it. Our draw method is ready. Let's use it in our code. Let's go back to the main file and call the draw method of the grid object we have created inside the main loop. So after the clear background dark blue method, we type grid.draw. Let's run the program. When we run the game, we can see a gray screen because all the cells are the same gray color and there is no visible space between them. To make the cells visible, we need to add a margin of 1 pixel to each cell. Our cell size is 30 by 30 pixels, so we can draw a 29 by 29 pixels gray rectangle for each cell to create the margin. This way, the grid lines will be visible, making the game more understandable and easier to play. Let's do it. In the draw method of the grid class, in the draw rect method, we need to make some changes. We need to add +1 here and here. This way, we add a 1 pixel offset at the x and y position of the gray rectangle we are drawing. Also, we need to subtract 1 pixel from the width and the height of the rectangle we draw because we said we need it to be 29 pixels. That's it. If we run the game once more, we can see that the grid lines are now visible. Beautiful. Our grid is visible. Now, let's modify the values of some cells to see if our grid can display them in different colors. So in the main.cpp file, outside of the game loop, let's hardcode the values of some cells as a test for our grid class. Let's set some values in the grid. Firstly, we will make the top left cell hold the value 1. grid.grid bracket 0 equals 1. I can duplicate this line by pressing Shift, Alt, and the down arrow key. Next, let's make the cell at the 4th row and 6th column hold the value 4, and the cell at the 18th row and 9th column hold the value 7. It is important to know that the counting for the rows and the columns starts from 0, so the 4th row is actually the row with index 3. Let's run the game again to see the changes we made. Great. Now we can see that the cells are displayed with different colors, indicating that the game is functioning as expected. Additionally, we can check the console to see the values of each cell, including the ones we have just changed in the code. Perfect, we have just completed step number 2. Congratulations on making it this far in the tutorial. You are doing great. Let's keep going and continue building our Tetris game. The next step is to create the blocks of the game. As you know, Tetris is a game where you have to fit different shapes made of 4 tiles each. There are 7 types of shapes in total, called tetrominos. When you start the game, the blocks appear in a certain way. The blocks in Tetris can spin around a point, usually in the middle of one of their tiles. For instance, the T-shaped block rotates around the center tile. The I block and the O block in Tetris rotate differently than the other blocks. The I block rotates around a point that isn't in the center of a tile, while the O block doesn't appear to rotate at all. To represent the blocks, we imagine a box around each block that's big enough to fit in all 4 rotation states. The box is divided into a grid, and we label the top left cell as the origin, row 0, column 0, just like in the game grid. For each of the 4 rotation states, we store which cells are occupied in this grid, not all the cells of the grid. Let's use an example to make this clearer. Imagine the T block in Tetris. We draw a box around it, and we divide it into a grid with 3 rows and 3 columns, making it 9 cells in total. However, we only need to store the cells that the T block occupies, not the whole grid. If the T block is in its first state, state 0, we only need to store the values 0, 1, which means that the cell in row 0 and column 1 is occupied. We also need to store 1, 0, 1, 1, and 1, 2 for the other occupied cells. We repeat this process for the T block's remaining 3 rotation states, storing only the occupied cells for each. This is how we represent all the blocks in Tetris, using this same process for each one. Using the bounding grid approach to represent the blocks has a big advantage. It makes rotating the blocks much easier. To rotate a block, all we need to do is to update a state variable that indicates the current rotation state of the block and modify the occupied cell stored in the grid accordingly. This means that we don't have to calculate the new positions of each tile in the block, which can be complex and time-consuming. Instead, we simply update the occupied cells in the bounding grid, and the game engine takes care of displaying the block in the correct rotated state. Okay, now that we know how to represent each block using the bounding grid approach, let's return to our code and start implementing it. Now, before we start coding, let's leverage an object-oriented feature to simplify our code: inheritance. Inheritance is like passing down traits from parents to children. C++ allows us to create a new class that is a modified version of an existing class. This new class, called the child class, will inherit all the attributes and the methods of the original class, called the parent class. Then we can add new attributes and methods or override the inherited ones in the child class to customize its behavior. This way, we don't have to repeat the same code for similar classes, and we can make changes to the parent class that will affect all the child classes. It is like having a template that we can reuse and modify without starting from scratch every time. In this game, we have 7 different blocks, but they all share some common properties and behaviors. Instead of creating separate classes for each block and duplicating the same code, we can create a base block class with the shared code and characteristics, and then create 7 new classes for each block that inherit from the base class. This means that each of the new classes will automatically have all the properties and behaviors of the base class without needing to repeat the code. Using inheritance helps us to simplify our code and make it more efficient. If you haven't used inheritance before, it's not a problem. It's actually a simple and powerful feature of object-oriented programming. Once you understand how it works in this game, you'll be able to apply it to other projects as well. Let's start by creating the block class, the base class for all the blocks. Let's create a new header file and call it block.h. Now, we type pragma once, class, block, curly brackets, and a semicolon, public, colon, and private, colon. Now, the first public method is going to be the constructor, so we type block, parenthesis, semicolon here. To create a block class, we need to determine what information each block needs to store. The most important thing is to distinguish between different blocks, so each block will have a unique ID. To add this attribute, we can create an ID attribute in the class, and we will make it public so we can access it from other classes. Int ID. To represent the cells that the block occupies in a 4x4 grid for all rotation states, we will create an attribute called cells. This attribute will be a map of vectors that will hold the position of each occupied cells on the grid. So we need to do some work before being able to create the cells attribute. As we said, we need a map of vectors. But what is a map in C++? In C++, a map is a container that stores elements in key-value pairs, where each element is associated with a unique key. It allows for efficient retrieval of values based on their corresponding keys. So we're going to use a map. The key is going to be the rotation state of the block, and the value is going to be a vector containing the positions of the occupied cells. Let's create a position class to make our lives a little bit easier. Let's create a new file and name it position.h. And now let's create the position class. This class will have a constructor that will take a row and a column as an argument. Pragma once, class, position, curly brackets, and a semicolon. Public, colon, position, parenthesis, intro, int, column. Also, this class will have a row and a column attribute, int row, int column. Now let's create the implementation file, Ctrl+N to create a new file and Ctrl+S to save it as position.cpp. Now the first thing we have to do is to include the header file, include quotes position.h. Now let's implement the constructor, position, position, parenthesis, int row, int column. This dash greater than row equals row, and this dash greater than column equals column. The this keyword is used to refer to the current object, and the this dash greater than, which looks like an arrow, is used to access a variable within the object. So this expression assigns the value of the row parameter to the row attribute of the current object. Similarly, this expression assigns the value of the column parameter to the column attribute of the current object. Cool, the position class is ready, and now we can represent a position on the grid with a single object. We can close this file now, and the position.h file as well. We won't need to open them again. Now we can finally create the cells attribute. As we said, it will be a map of vectors, so in the block.h file, let's include these classes. Include vector and include map. Lastly, we need to include the position class we just created. Include position.h. Now let's create the attribute, std::map. The map will contain a key, which will be an integer, so int here, and the values which will be a vector of position, so comma std::vector position cells. Next, we need to know the size of each cell of the block in pixels. So the next attribute will be a private one, int cell size. The next thing we need to know is the rotation state of the block. So let's create a new private attribute named rotation state, int rotation state. The last thing we need to know for the block for now is the colors it has to use to draw each occupied cell on the screen. The colors are the same ones we used in the grid class earlier, so we can copy the method from the grid class and paste it in the block class. However, this will result in duplicate code, which is not a good programming practice. We want to avoid duplicate code as much as possible to keep our code organized and easy to maintain. So we will create another file to hold all the definition of the colors and use it in both the grid and block classes. We press Ctrl+N to create a new file and Ctrl+S to save it as colors.h. Now we type pragma once. We also need to include Raylib since we will be using the color struct from it. Include Raylib.h. Now let's declare all the colors. Let's do the first one. Extern const color dark gray. Using the extern keyword allows us to declare a variable in one file and use it in another, making it easier to share data across different parts of our program. The const keyword specifies that the value of the variable cannot be changed during program execution. Similarly, we declare all the colors we use in our game so far, like this. Now let's define all the colors in a .cpp file. Let's create a new file and name it colors.cpp. We have to include the header file, so include colors.h. Now let's copy the color definitions from the grid.cpp file. I just copy these values and I paste them here. Now all I need to do is to add the const keyword at the beginning of each color definition. Perfect. Now let's create a simple function that will return a vector with all the colors in a specific order, just like we did in the grid class. std::vector color getCell colors. And we simply return a vector of all the cell colors. We use the same return from the getCellColors method of the grid class. We can simply copy it from the grid class and paste it here. Cool. The last step we have to do is to define this function to the header file. We go back to the colors.h file and we type std::vector color getCellColors parenthesis and a semicolon. And since we are using the vector class, we have to include it. Include vector. We are now ready to use our colors.h header file in our code. First of all, let's use the colors header file in the grid class in the grid.cpp file. Let's include it. Include colors.h. Now we don't need the getCellColors method anymore, so we can remove it. We also have to remove the method declaration from the header file. So we open the grid.h file and we remove the method declaration like this. Now, back in the .cpp file, in the constructor, we don't have to change anything. The getCellColors function now lives in the colors.cpp file. Our grid class is ready. Let's run our program again to see if everything works. Cool, our game works with the new colors header file just like before. Now let's go back to the block class. First, we are going to include the colors header file. Include colors.h. As we said before, we need a colors attribute. Let's create it. std::vector color colors. Now we are ready to implement the constructor of this class. Let's create a new file and call it block.cpp. First of all, we type include block.h to include the header file. Now we type block::block parenthesis and curly brackets. Let's initialize some of the attributes. We won't initialize the ID in this class. We will do this in the child class. We will initialize the cell size. Cell size is equal to 30. We will also initialize the rotation state. Rotation state is equal to 0. Lastly, we will initialize the colors vector. Colors is equal to getCellColors. Perfect. That's it. We now have a vector containing all the colors we need to use to draw a block on the screen. The block class will also have a draw method that will be responsible for drawing the block on the screen. Let's create this method. Void block ::draw parenthesis and curly brackets. VS Code underlines this method because we haven't declared it yet in the header file. We select the Quick Fix button here and we let VS Code create the declaration for us to save some typing. Cool, it automatically declared the method. Now let's go back to the block.cpp file. Now we need the position of each occupied cells of the block in order to draw it on the screen, but we don't have this information yet, so we have to create it. To simplify our code, we will use inheritance. We will create a separate class for each block, which will contain the cell positions for each rotation state. These classes will inherit from the block class. Let's create a new file and let's name it blocks.cpp. Inside this file, we will create all the child classes, one for each block. First of all, let's import the two required classes, include block.h and include position.h. Now let's create a class for the L tetromino. Class lblock, curly brackets, and a semicolon. As we said, this block must inherit the attributes and the methods of the block class. So we have to declare that here, public block. Now the lblock class is a child of the block class. Now let's create a constructor for this lblock class, public lblock parentheses and curly brackets. Let's give this block a unique ID equals 1. Now all we have to do is to define which cells are occupied. We are going to use the cells attribute of the block class. As we said, the cells attribute is a map of vectors. The key of this map will be the rotation state, a value from 0 to 3. So the map is going to have 4 keys. Let's do it. The first key is going to be 0, so we type cells bracket 0 equals 2. Now we need a vector with all the occupied positions of the L block in the rotation state 0. Which cells are occupied when the L block is at the rotation state 0? Cells 0, 2, 1, 0, 1, 1, and 1, 2. Let's create a vector with these cells using the position class. Curly brackets, position 0, 2, position 1, 0, position 1, 1, and position 1, 2. That's it. The rotation state 0 is ready. Now we need to do the same thing for the other 3 rotation states. I will leave this as an exercise for you to practice. Based on the given graphic, please fill in the missing data. Take your time to work on it, and when you are ready, you can resume the video to see the solution. Welcome back! I hope you were able to successfully complete the exercise and that it helped you better understand what we are doing. So that's the complete class. I have filled in all the data for all the rotation states. We have to do the same thing for all the blocks. But before that, let's draw the first shape on the screen. Let's go back to the block class and work on the draw method. Now we have access to all the cells of the block for every rotation state. Check this out. std : vector, position, tiles, equals to, cells, brackets, rotation state. This line retrieves the vector of positions for the current rotation state of the tetromino as determined by the value of the rotation state attribute. Since the rotation state is now 0, we get the vector that corresponds to the key 0 of the cell's map. Now, for each cell, we can draw a rectangle. We're going to use a for loop. For position, item, tiles, curly brackets. Now, we need to create a rectangle for each cell. For this, we're going to use Raylib and the draw rectangle function. Draw rectangle, parentheses, x, y, w, h, color. Again, we need the x and y position of the tile we are going to draw. Item.column times cell size plus 1, item.row times cell size plus 1, the width and the height will be cell size minus 1. As we did in the grid class, we leave a 1 pixel offset when we draw the cells. That's it. The color value of the cell is obtained from the colors vector using the block's ID as the index. Cool. Let's now use this method and see a block on the screen for the first time. Back to the main.cpp file. Include the blocks file. Include blocks.cpp. Now let's remove the following lines of code from our main file since we use them for testing purposes only and they are not needed anymore in our final implementation. Now let's create an L block. L block is equal to L block, parentheses and a semicolon. Now in the game loop, let's draw this block by calling the draw method. Block.draw. Let's run the game. The L block has appeared on the screen. How exciting! After all the code we have written, it's rewarding to finally see a block rendered on the screen. If you have made it this far, congratulations! You have accomplished the most challenging part, and things will start to progress more quickly from now on. Now we need to create classes for the remaining 6 blocks of the game. To do this, we will go back to the blocks.cpp file, and we will create a separate class for each block, such as the I block, the J block, the S block, etc. For each class, we will define a unique ID and the positions of the occupied cells for each rotation state, similar to what we did for the L block. Once we have all the block classes defined, we can easily create instances of each block type in our main program. As an exercise, take a moment to write the remaining classes yourself. I will provide you with all the data you need for each block. Simply
This is the game that you and me will be making together in this video, and I will walk you through the entire process of picking the art, to publishing it, and everything in between, split into multiple steps. Along the way, I will show you various tricks and game programming patterns. The hardest thing about game development in C++ is by far starting, and it took me literally months. But you will have overcome this step in one day by the end of this video. So let's start. The first step is to learn the language, and if you already know C++, don't worry, I'll keep this point very brief. Basically, you can start with any tutorial because, trust me, they're all the same, and learn the basics like up to classes, templates and STL containers. After that, start making projects rather than learning advanced stuff. Complete challenges on Codewars or make console apps. You will learn more by doing stuff than learning advanced language features. If you want more details, check out my videos on this topic. If you are still a beginner, I recommend watching this video anyway, because it is made to give you the motivation that you need, and you will also get some nice tips related to more things than just programming along the way. Step 2. Game math. If you are not a math fan, don't worry, this step will also be brief. You just need to understand what a vector is. So a vector is just a point into your 3D space. So for 2D, it has two components, x and y. It can describe many more things however besides a position, like a direction or a force. Now adding two vectors looks like this. If you want to subtract, you can just flip the vector subtracted, and then perform normal addition. So let's say this is an enemy ship, and this is our ship. We want a vector pointing from the enemy to the player. So to do that, all you have to do is take the player's ship position and subtract the enemy's ship position from it. Now this is the direction to the player. Usually for directions, we normalize the vectors, and that just means we make the vector's length be size 1. We do that simply by dividing
close till I get up. Time is barely on our side. I don't wanna waste what's left. The storms we chase are leading us, and love is all we'll ever trust. Yeah, no, I don't wanna waste what's left. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. Finding life along the way, melodies we haven't played. No, I don't want no rest. Echoing around these walls, fighting to create a song. I don't wanna miss a beat. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go.
I'm walking alone, the streets are empty. The only thing I can see is my own silhouette. I'm getting stronger, step by step. The clock is ticking, but there's no time for regrets. I've been flying from town to town, from London to Taiwan. I've been all around the globe, trying to protect your soul. We are heroes tonight. We will fly above the sky. We are heroes tonight. Yeah. town to town, from London to Taiwan. I've been all around the globe trying to protect your soul.
invincible.